What is the best way to tune PID controllers? Imagine trying to balance a broomstick on your hand without it falling over. That's similar to what tuning a proportional integral derivative controller involves. It's about finding the right settings so your system responds smoothly and accurately. Tuning a PID controller is all about adjusting three key parameters: proportional gain, integral gain, and derivative gain. These control how the system reacts to errors between what you want and what you get. Proportional gain controls how strongly the system reacts to current errors. If you make it too high, the system might respond quickly but could overshoot and start oscillating. If it's too low, response might be slow and sluggish. Integral gain works on accumulated past errors, helping to eliminate steady errors that never quite go away. But if you set it too high, it can cause the system to become unstable or respond too slowly. Derivative gain predicts future errors based on how fast the current error is changing. It helps to smooth out the response and reduce overshoot. There are a few common ways to tune these parameters. Manual tuning is straightforward but requires patience. You start with all gains at 0. Increase the proportional gain until the system responds quickly but begins to oscillate. Then, add some integral gain to fix any steady errors. Finally, tweak the derivative gain to reduce oscillations and improve stability. It's a trial and error process but works well when you understand your system. Another popular method is the Ziegler-Nichols approach. Here, you set the integral and derivative gains to 0 and slowly increase the proportional gain until the system oscillates steadily. The gain at this point is called the ultimate gain. The period of oscillation is the ultimate period. Using these two numbers, you can calculate initial values for all three gains with simple formulas. This method gives a good starting point but often needs refinement to prevent overshoot or instability. The Cohen-Coon method is another option. It uses the system's open-loop step response to estimate parameters. You look at how the system reacts to a step input and identify key points on the response curve. This method is especially useful for systems with significant dead time or delay, giving better initial tuning than Ziegler-Nichols in those cases. Today, many engineers turn to automatic tuning tools. Software like MATLAB's pidTuner can analyze your system model and automatically suggest optimal PID parameters. These tools save time and often produce more balanced responses, especially for complex or sensitive systems. In robotics or mechanical systems, the choice of tuning method depends on how much control you have over the system and how quickly you need results. For precise robotic arms, automatic tuning or refined manual tuning works best. For simpler systems like temperature control, classical methods or manual tuning are often enough. In the end, the best way to tune a PID controller is to understand your system's behavior first. Then, pick a method that fits your needs: manual, classical, or automatic. Adjust the gains carefully and test the response. Keep refining until you get a stable, fast, and accurate system. That's how you get the most out of your control system and keep everything running smoothly.